Welcome to Talks with Dr. Gupta and friends. Today, let's talk about quantum computing and its role in artificial intelligence. For almost a century, quantum mechanics has been one of the deepest mysteries in science. A theory so powerful, yet so strange, that even its creators struggled to accept it. But right now, we are on the edge of turning that mystery into a technology, one that could literally change the world. So let's get into it. Quantum mechanics isn't just a new set of rules. It's a completely different way of seeing reality, one that clashes with our everyday intuition. To understand where quantum computing is going, we need to go back about 100 years. In the 1920s and 30s, physicists like Heisenberg and Schrödinger uncovered a bizarre new layer of the universe, a world where certainty disappears, outcomes are probabilistic, and particles behave in ways that defy common sense. Even Albert Einstein was deeply uncomfortable with what they found. He famously called it spooky action at a distance. So what exactly makes the quantum world so weird? It comes down to three ideas: probability, superposition, entanglement. And here's the key point. These aren't just abstract theories anymore. They are the tools we use to build quantum computers. First, probability. In our classical world, probability comes from ignorance. A weather forecast is uncertain because we don't have perfect data. But in the quantum world, randomness is fundamental. Even if you knew everything about a particle, you still couldn't predict the outcome with certainty. Uncertainty is built into reality itself. Second, entanglement. Two particles become linked in such a way that measuring one instantly tells you something about the other, no matter how far apart they are. Think of a book. In a normal book, the story is written on the pages. Page 1, then page 2. But in a deeply entangled quantum book, the information isn't on any single page. It's hidden in the connections between pages. Read one page alone, and it's meaningless. Third, and most important for computing, superposition. A classical bit, the kind in your phone, is a simple switch, 0 or 1. A quantum bit, or qubit, can be 0, 1, or both at the same time. It's not a switch, it's a spectrum of possibilities. Here's why that matters. With 10 classical bits, you can store exactly one number between 0 and 10 to 3. You must choose one, but with 10 qubits, you can represent all 1024 possibilities at once. That's where quantum power comes from. Scale that up to hundreds of qubits, and the number of possible states becomes so large that describing them would require more classical bits than there are atoms in the known universe. Mind-bending, but fragile. Because here's the catch. Quantum states are incredibly delicate. Their enemy is decoherence, a vibration, a tiny bit of heat. Any interaction with the environment acts like a measurement, collapsing the quantum state and destroying the computation. So how do you protect something so fragile? The answer is one of the most brilliant ideas in modern physics: quantum error correction. Instead of storing information in a single qubit, you spread it across many physical qubits. You hide the information in entanglement. So when the environment disturbs one qubit, it finds nothing. The real information, the logical qubit, remains safe. The challenge is enormous. Today's best physical qubits might fail once in 1,000 operations. A truly useful quantum computer needs errors closer to 1 in a billion. That gap defines the race. Now here's the crucial question. What does any of this have to do with AI? Because quantum computers are not meant to replace your laptop. They won't help you check email faster. They're designed for very specific problems, especially problems where nature itself is quantum. And this is where AI enters the story. Modern AI is hungry for ground truth data, especially in areas like drug discovery, materials science, batteries, chemistry, and climate solutions. But classical computers struggle to simulate quantum systems accurately at scale. Quantum computers don't. So the real breakthrough isn't quantum replaces AI, it's a partnership. Quantum computers simulate molecules and materials with high fidelity. That produces extremely accurate data. AI trains on that data. AI then discovers better drugs, better materials, better solutions. Quantum becomes a truth engine. AI becomes a pattern engine. Together, they form a powerful flywheel for scientific discovery. We are standing at the dawn of a new era of computation, one that won't just answer questions we thought were unsolvable, but will force us to ask entirely new questions about the universe itself. And if quantum computing can finally unlock nature's deepest secrets, what should we ask it to solve first? Happy new thinking!